Thanks. I really love this place. I think many of you have been in the previous two lectures. We were looking at this computational lens on things, on lots of issues that were studied in many disciplines over, for many reasons over a long period of time. And sometimes this computational view adds another dimension, or suggests a new definition that in some cases is even useful for a variety of applications. We saw this happen with scientific models and mathematical proofs. We saw that notions like proof can have different meaning and different properties when you are restricted computationally, like zero knowledge. We saw that secrets can be exchanged in situations where you might not imagine that they can. So many basic notions come into display. That's what we like to study in the computational complexity. And what I want to tell you about today is one of my favorite topics. This is randomness. And the title here is Randomness and Pseudorandomness. We'll get to see what exactly I mean by this. But even randomness is not something for which there is a consensus about. And of course, it's in some sense a notion that people outside of academia, everybody, children, have some opinion or experience with it. You talk about luck and chance and various things happen at random where you don't define it mathematically, certainly. And even among the approaches, the mathematical approaches to randomness, there are very many different ones. So I'm going to tell you today about the computational one. So, as usual, here is the plan. And we will talk only about discrete events. So, discrete events, the most basic random event is a one-bit event. You toss a coin and it comes up either heads or tails. Okay? Now, suppose that it's a perfect coin and it comes up heads or tails exactly with probability 50%. Then which do you think is more likely outcome of 20 coin tosses? The first one or the second one? Everybody agrees. So I just want to make sure that everybody agrees. Both of them in this world, they have the same probability, 1/2 to the 20. So that's important. That's called the uniform distribution on sequences. That's what I would call basically a random event. And what we will see is that the ability to have such random sequences is amazing. I mean, you get a lot out of them. Some of these examples you will have seen, and some of them maybe you haven't seen. I'll just give you lots of examples to show that, randomness is really, really useful. And then we'll ask ourselves, can you really use it? I mean, where do you get these random bits from? Okay? That will be a fundamental question. And in order to answer it, I'll explain some rudiments of the theory of pseudorandomness. And pseudorandomness studies deterministic structures without randomness, which seem to have some properties that random structures have. Some properties, maybe not all, but maybe the ones that we care about. And that will be pseudorandomness, and we'll see lots of examples and applications of this. And finally, this will help us to understand how can we, achieve some of the applications of true randomness when we don't have it, or when we have little of it. Okay, so that's a plan. So first I'm going to show you just a bunch of examples where randomness is useful. And in all of them, you just should, in the back of your mind, you should say, wait a minute, where are these random bits coming from? Do we really have this application or not? I'll remind you, this picture will keep appearing, so to remind you not to forget that it's a non-trivial assumption that we have perfect randomness. Okay, so the first one, which you all know and you see everybody every day on the newspaper, especially in election time, is sampling. So you want to estimate, let's say this is in the United States, you want to know in the coming elections how many will vote Republican, how many will vote Democrats. You don't go around asking all of them. You just take a random sample, completely random sample. If you take 2,000 people instead 280 million, which is the population, here's what you get. And this is, I think, still, despite the fact that it has a simple proof, and I taught it many times, and it's still, I find, remarkable. What it guarantees, this random sample, is that with probability 99%, so all but 1% of the samples will have the property that the average they give you about the actual vote, about the numbers who will vote red and blue, is the same percentage as in the true population within 2%. And in fact, this number 2,000 remains 2,000, doesn't matter if you have the population of the US or that of France or that of China, or it's just the number of atoms in the universe. It doesn't depend on it. So it's an extremely powerful result, mathematical result, and of course it's used all over the place. We use sampling everywhere. Of course, in science, sampling is very important. If we didn't have this randomness, there is no other way but go and ask roughly all the population. If you want within 2% to be accurate within 2%, you have to ask 98% of the population, which is huge. Okay, so that's great, and that's the question you should remember. Can we really do it? Certainly not how they do it in public, in polls. Okay, here's a completely, and I do really very different applications. Here's another very different application. That's the use of randomness to efficient algorithms. So I talked in the first lecture about efficient algorithms and their importance. And it turns out that at the time, on Monday I talked just about deterministic algorithms, but you can take algorithms, Turing machines, and allow them to toss coins. And then they can do remarkable things that maybe cannot be done deterministically. So that's an example. What's the problem here? You are given a region in space. Physicists would know it. And you ask, in how many ways, it doesn't have to be a square region, it can be any shape. And you ask, in how many ways can I tile it with dominoes, with 2x1 dominoes? Okay? And if this is large, then the number of possible tilings is exponentially large. So it's really a difficult problem. It's a really interesting problem. It's a monomer dimer, I guess it's the dimer problem. And it has to do with, it's really important for chemistry. It captures the thermodynamic properties of the matter, the material you are talking about. And that's why it's interesting. And the question is, well, how to do it efficiently? So it turns out that there is a result which gives efficient probabilistic algorithm, so a polynomial time algorithm using randomness, that gives you approximates this number to very, very high accuracy. And this algorithm, of course, I'm not going to describe it. It's quite sophisticated, but for those who know, it follows this paradigm, which is often called Monte Carlo method, that von Neumann and Ulam developed in the context of the nuclear program. And that's if you have randomness. If you don't, the best we know, the best deterministic algorithm we know is exponential time, so completely useless. I should stress that that's the best algorithm we know. Maybe someone tomorrow will find a better one, but as far as we know, deterministically it takes exponential time. So we have here an exponential gap between what randomized algorithms can do and deterministic algorithms can do. And this is not the only example. There are hundreds of examples. So randomized algorithms are extremely important because they provide the only way that we know how to efficiently solve problems that we want to solve. So we have this, and you can ask yourself, where is the randomness coming from? Again, here's a very, very different example. It comes from the field of distributed computation. It's an allegory, of course, to capture some real systems problem. So it's called the dining philosopher's problem, this one. And what it's trying to capture is a competition over resources in a world in which you don't have shared time. Everybody have their own clock. and some adversary controls the rate of this clocks. What you basically, it's not too important. The basic idea is that, you know, they're all sitting down to eat. You may recognize some of them. To eat, everyone needs 2 forks, okay? Each of them gets hungry in different times, and but they all need to eat something, sometimes, even philosophers. And the thing is, how do you program them so that, you know, each of them will get to eat, and each of them, you know, but will not block others' way. So if you tell all of them, so they are identical, despite the pictures are different, but you want to give them each, you want each to be a computer program, the same computer program. So if the program says, you know, you want to eat, take the right fork, then take the left fork, you see what will happen if they all want to eat at the same time. And basically, it's a problem of symmetry breaking, and Dijkstra, who proposed this, you know, this situation, and many others in distributed computation, proved that in this setting, there's just no deterministic way to do it. There's no program that you can give each of them that will guarantee that they will all eat when, you know, eventually. Whereas if you allow randomness, Lehman and Rabin gave an algorithm which, you know, does it. So there is again a discrepancy between the deterministic and probabilistic world. And what randomness is used in this context is to break symmetry between, to break the, you know, sort of create identities where there are none. So that's another one, and that's another one for which, you know, we need pure randomness. Now, the previous 3 examples are about doing something. And they each come with a, you know, each describes many other situations when you want to do something. But sometimes randomness is essential even just to define something, just to have a meaningful mathematical notion. And I'll give you 2 examples. One comes from game theory. I'm sure many of you have seen this. So how is a game described? A game is usually described, let's say in this case, a game between 2 players. This is called the chicken game. Describes a situation where, in this case, every player, the row and the column, have a, you know, 2 possible strategy, and this describes, well, if the first player plays this and the second player plays this, what each of them gets, you know, $1 or something. This particular game is best described as, you know, this kind of 2 drivers driving towards each other, and, you know, they see each other. The question is, it's called the chicken game because you see who will swerve to avoid collision first. This is a chicken. Of course, you know, if they both are chicken, then fine, they save face. But if only one of them, then you know, then maybe suffer socially. But if they are both, aggressive, then you know, they may die. So this maybe should be a higher number. Anyway, you have this kind of game. You can imagine lots of other games that arise. Those who know game theory, you know that there are lots and lots of them, and they capture interesting situations in war, in government, in politics, in economics, between companies competing, and so on. So it's really interesting. And the question is, what should players do in this situation? What will describe a rational behavior for a player in a game like this? And John Nash, in the work that he got the Nobel Prize for, described what is a rational solution, what's called the Nash equilibrium. A Nash equilibrium is a choice of strategy for every player, so that for every player, if, you know, he knows or the other strategies are fixed, he has no advantage to change his. It's sort of a stable collection of strategies. And okay, it's a definition, so it's not clear it's useful. And it's not clear which games possess such an equilibrium or which not. And it turns out, Nash proved, that every game, doesn't matter how many players, has an equilibrium. Doesn't matter how many strategies. Every finite game has an equilibrium. It's a great result. That's a Nobel Prize type of result. And this proof works if you allow, if and only if you allow mixed strategies, namely random strategies. Okay, so in this particular game, the stable choice is for each player to choose to be chicken with probability 3/4, to choose to be aggressive with probability 1/4. If they are allowed to do that, then there is always an equilibrium. If they are not, then there may be no equilibrium. In this case, there is no equilibrium. So randomness here guarantees the existence of an object that wouldn't exist otherwise, and a very important object, rational behavior in this case. Okay, if they want to play it. And finally, we saw, on Tuesday, lots of examples where randomness is used. Secret cannot be defined without randomness. I mean, Shannon proved that, basically a secret is as good as the entropy, the randomness in it. So if you pick a 9-digit number as your password to somewhere, if you pick it randomly, then the chances of guessing it is exactly 1 over a billion. But if you choose it just as among the phone numbers of your friends, then it will be easier to break. So it's just how much randomness there is there. And then there are lots of other things that we talked about on Tuesday in the cryptography lecture, which are all applications of in cryptography, and all of them require randomness. It's essential to have randomness for them. And again, where is it coming from? There are other applications of randomness that you all know and love. So let me get to the main point. So where are random bits coming from? In fact, I'm sure many of you are using them. So where are they coming from? So I don't know about you, but when I want to know something by now, there's only one way to know something. You ask Google. Where do random bits coming from? Which I asked, and that's the answer. So the answer is you buy them. I mean, that's where they come. You buy them. You want them, you just buy them. And notice that this is just the first page. I think there are about 4 million ways to buy them. Maybe it's not always companies, but there are many companies who sell random bits. It's a money-making business. Obviously, because people need them, right? So what do they base their randomness, how do they generate? So you go and look, and this guy uses radioactive decay, and these guys look atmospheric noise. These guys, both of them use measuring photons. They all, have their ways of generating. So they all try to tap some kind of physical phenomena which seems somewhat unpredictable. Maybe does something to it, etc. So is it good or bad? Is it useful? Is it random? Okay. So now we come to the most important slide of as usual, I'm giving you a warning about the slide to listen to. We want to define randomness. And I want to, why is this a key slide? Because you go to the dictionaries, you go to the mathematical books, you go everywhere, and there are many definitions of randomness, but they are always objective. They always define randomness as a property of what has happened, or what can happen. And I want to just change your opinion about this. I want to convince you that randomness is subjective, it's not objective. That's absolutely key to understanding the rest. Okay, so what do I mean by that? So let me pick a victim here, Matthias. Okay, so we'll do now just do an experiment with me. I'll take a coin out of my pocket. It's a coin, and sorry, Matthias, that's you. And here's what we are going to do. I'm going to toss, I don't have to do it, I will just have to see what, but the idea is that the experiment is that I toss my coin, and just as it's in the air, like here, you are supposed to guess what is, what will it come up, heads or tails. So if we did it, what is the chance you'll guess correctly, you think? 50%, good. So, I agree. I think everybody would answer the same. That's what the best chance you'll have. Okay, so that's experiment number one. Now let's do it again. Just change a little bit the game. I'm going to give Matthias a laptop. I mean, I can't give you the laptop. Imagine you had a laptop and we were playing the same game. What do you think is the probability you'll succeed in guessing the outcome? 50%. I think so too. I mean, if anybody objects. So okay, now let's enhance it even better. I mean, Matthias deserves more. So let's give him a few video cameras here around the room. Let's connect them to a Cray computer and connect all this machinery to his laptop. And it's all ready and in place before I toss my coin. And now I'm going to toss it and ask him what's the probability you can guess of the value of the coin when it lands. I swear we didn't talk about this before, but in fact, you know, these are the answers everybody gives, and that's what I would give. It makes perfect sense because now, with all this machinery, you know, the coin just starts spinning, and there is enough information and time to evaluate its momentum and the air humidity and whatever you want. And well, three. I mean, for the skeptics, I will say you toss it from the top of the Empire State Building and you have a minute, okay? That's not the point. But if actually it will work. But what is the point? The point is that what I did didn't change. I still toss the coin. This is the random event. And nevertheless, the randomness in it changed with the computational power that Matthias had. So randomness is somehow in the eye of the beholder or in the computational power of the beholder. It depends on the subject using the random event as opposed to on the coin. Okay, so that's really an absolutely key point. So it's an operative, it's a subjective definition of randomness. It's how random something is depends on the power or the application using it. That will be absolutely key. So now we are ready to look what pseudorandomness is. That's exactly what pseudorandomness is about. It's about what are the properties we are trying to get out of the random event, how are we using it, what kind of computations we do when we use it. So it's a study of deterministic structures that has some random-like properties shared by random objects. And it turns out that different properties correspond to different applications. So pseudorandomness is a very rich world. And it's really interesting that it's being studied both in mathematics and computer science, but somehow with different attitude. Naturally, in fact, with different attitude. In mathematics, most of this study looks at random-like properties of natural structures that exist in mathematical structures. Whereas in computer scientists, usually you know what properties you want, and all you want is to create that structure. It doesn't have to be natural necessarily, but you want to create it efficiently. But these two approaches go very well hand in hand, and it's there's lots of common work between mathematics and computer science on this area. Mark mentioned in the first day the work on expanders. Expanders is a very important joint area between them on a pseudorandom phenomena. But I want to start giving you examples of pseudorandom objects so that you get a feeling for it. And this is maybe the simplest. So I'm assuming you all recognize this number. It starts 3.14. But anyway, it's a decimal expansion. And I'm using it to define a property of numbers, of such real numbers. And here's what I want. What I want is that every digit, let's say 7, will appear 1/10 of the time because there are 10 digits. I want that every 2 digits will appear consecutively 1/100th of the time because there are 100 pairs. I want that every triple will appear 1,000th of the time, and so on. This will certainly happen for a random sequence. This will happen. So a number in this case is pseudorandom if it happens for it. And of course we go on and on for any sequence, but I want it not just in the decimal system. I want it to hold no matter in what base you represent this number. So when you write pi in decimal, this holds. When you write it in binary, the same thing holds, but now you have 2, 4, 8, and so on. Okay, so if a number has this property, then we call it a normal number. This was defined by Borel, who proved, and that's not a difficult proof, that a random real number is normal with high probability. So almost every infinite sequence like this you pick will have this property. That's great. So what can we ask? So what do we want? The random one has it, but we are looking for a number like pi, or asking ourselves, is a number pi normal? It's an open question. It's actually a very famous and important open question. And similarly, you can ask about other numbers, square root of 2, it's unknown. So this is a pseudorandom property, but of a type that we don't have really good examples of deterministic structure that has it. But the definition should be clear, right? A number doesn't have to be random. It can be pi, which is well defined. It's the ratio of circumference to diameter of a circle. And despite that, people believe it's normal. So it can be pseudorandom in this sense. So here the sense is a bunch of conditions. Okay. Now, I'll talk about some other pseudorandom phenomena, but I want before this to really convey to you how important pseudorandomness is, even though it may not be evident when you first look at some important problems, that they can be stated in terms of understanding pseudorandomness in some sense. So, and the problems I want to, you have seen this list, many of you have seen this list in the first talk. You know, in order to convince you that these problems are important, I again remind you that these are in the list of problems that Clay Foundation offered $1 million for, and that one was taken. But now I'm using it for a different purpose. So these two problems on the list, the P versus NP problem we talked about, and the Riemann hypothesis problem we did not talk about, are questions about pseudorandomness. So I want to explain this. Now about P versus NP, I will not really explain it, both because we talked about it and because it's a little longer to really get the details, but the highlight is the following. Random functions are hard to compute, okay? So our pseudorandomness property is being hard to compute. And the P versus NP question is prove this kind of pseudorandomness, namely hardness to compute, for some concrete problems, like the traveling salesman problem, or Sudoku, or map coloring, the problems we talk about. So if you can generate, like if you know, with the question whether pi is normal, the question whether the traveling salesman problem is hard to compute, that's P versus NP. So it's a problem about, and it's pseudorandom because random functions have this property. They are hard to compute. Okay, so that problem is about pseudorandomness. Why is this problem about pseudorandomness? So this I will explain. I think not too many people, even in mathematics, know it. It turns out that it is about, well, let me do it in detail. It has to do with random walks. So let me tell you what is the pseudorandom property, and then we say how the Riemann hypothesis, which is the most famous and maybe most important open question in mathematics, related to pseudorandomness. So it's about this random or drunkard walk. So what's a drunkard's walk? It's someone who starts here at point 0, maybe there is a pub there, goes to the pub, have a few beers, and then comes out, and then, you know, goes one step up or down, each with probability 50%. And now it does it again and again and again. And let's say it takes n steps. How far will it be from the origin? So it's a bunch of experiments which you do. And of course it doesn't prove it, but it suggests it. You look at them, and there are 100 trials for each. And in each of them, you see how far the guy is from the origin. It's about 10 or 20 steps, despite the fact that he's taken 100. And in fact, it's not very difficult to prove that almost surely, if you really take a random walk, almost surely after you do n steps, you will be only at the distance square root of n from where you start. That's not difficult to prove. Anyway, it's a fact. So this is a pseudo-random property now of walks. We had properties of numbers, properties of functions, properties of walks. The structures can be different. So the pseudo-random property of walks is being close to the origin. You walk n steps, you are within square root n roughly of where you start. So here's a deterministic walk. So like before, we had for normal numbers, we had pi. For hardness to compute, we had traveling salesman. Here we again are suggesting a deterministic structure and asking ourselves, is it pseudo-random in this sense? So what is a Möbius walk? Let me first define for an integer x, p of x to be the number of distinct prime divisors of x, okay? And then this mu of x, which is just gives you a value for every integer, 1, -1, or 0. So in this walk, you are allowed to stay in place. So it's 0 if x has a square divisor, and if it doesn't, you just count. If the number of divisors is even, then it's 1. If the number of prime divisors is odd, then it's -1. So you can think of, here is the values for the first few integers. So here are the first few integers, and you see their Möbius value. So you can interpret this value as a walk. It tells you whether to go up or to go down or to stay in the next step, okay? And you can ask yourself, does this walk stay close to the origin? So here's an amazing fact, proved by Mertens. The following two conditions are equivalent. That this walk, the Möbius walk, stays close to the origin, and the other equivalent fact is that the Riemann hypothesis is true. So it's a completely, elementary, first of all, and pseudo-randomness-like way to define this very famous, if you never knew it and you thought it's really hard to explain to someone, when it's not. That's the Riemann hypothesis. That's all you need to do. You just have to prove that this walk stays close to the origin. Okay, so we saw already a couple of examples, and in particular that pseudo-randomness occurs in fundamental problems. Let me now switch. We'll see some more properties soon, but I want to talk about the goal of this, which we talked about in the beginning. How do we cope with with a world in which there is no randomness at all, or maybe there is a little randomness? So I have to explain what little randomness means. So if we don't have perfect randomness. So actually we'll explore a bunch of possibilities. You can think of, we started the talk with a full gas of randomness, and now we are starting to lose it. So we'll look at a world in which there are weak random sources, like we talked about, the ones used by the companies selling them. And we'll distinguish two situations, one in which you have many or several independent sources of randomness, and one which is weaker, in which you have just one. All the randomness in the world is correlated. And then we'll get to the worst possible world in which you have absolutely no randomness. The world is deterministic. And we'll ask ourselves, which of the applications I showed you in the beginning survive in such worlds, where we don't have what we assume? Okay. So so the game is, we have all the applications I talked about and many I didn't talk about, in which the assumption is that you have perfect, mint gold coin toss as a uniform distribution. And now assume that in our world, we just have some phenomena that seem unpredictable somewhat. And there are many examples like this, right? We mentioned some here, the sunspots, and we have stock market fluctuations, and we have radioactive decay, and all of them seem to be somewhat difficult to predict. Right? With the stock market, you know it. Yeah, it's the same, and many, many others. Okay, so the question is, can such weak randomness be utilized? Weak, I mean, maybe the sample, so you can sample any such phenomena and you can also generate bits, but they may be biased as opposed to unbiased. They may be correlated with each other, right? The weather tomorrow with high probability will be similar like today. At least that's the best guess you have. That's definitely not independent of what it was today. So it's so on. So the question is, what can you do with these lousy coins, antique coins? And this is a subject of what we call extractor theory, which is very developed theory in pseudorandomness, and I'll tell you some about this. Okay, so I'll tell you some about this. So we start with a situation where we assume that these kind of events, this somewhat random events, are independent. Somehow you have to assume, for what I'll say first, is that sunspots don't affect the stock market, although some people believe that they do. So for this, we will need a different pseudorandom object. Okay, we need pseudorandom tables. So since pseudorandom works and pseudorandom functions and pseudorandom sequences, normal numbers, and so this is about pseudorandom tables, two-dimensional tables. Okay, so in a random table, so if I pick just a table of random, I don't want to be precise about the definition, but if I just generate these numbers in these entries, at random from some range, then what will happen if I look at a window which is not too big, right? Then what I expect is not to find too many collisions, I don't expect to find the same number occurring many, many times. This is a property that you can check if we appropriately choose them. So in a random table, you look at these windows, every window, in a random matrix, every window is rich. It has many, many different entries. In particular, rich, if the matrix, this window size is k by k, it doesn't have to be contiguous. If you pick, k rows and k columns and look at what they define, I want to talk about this kind of matrices also. So every k by k matrix will have between 0 and k squared possible different numbers, and I will call it rich if it has just a little more than linear, k to the, let's say, 1.1. You don't have to remember it, but just that there are a lot of distinct entries. That is a property of a random matrix. Okay, random table. So the question is, as before, can we exhibit deterministic structures that are random in this sense? So that's a question. Can we generate them, or are they, Okay, so we have this question, and you start thinking, like with weird-looking numbers, you immediately think about E. With the hard functions, you immediately think about your favorite, like traveling salesman. With tables, I don't know what you think. But let me start from first grade. So, you can look at the addition table. That's something we learned. We have known for many years, and you can ask yourself: is this pseudorandom in this sense? Is every rectangle here, every window rich? Yes, no? No. Yeah, so, if you look at, this consecutive rows and columns, or in fact, you can take arithmetic progressions in the rows and the column, then it won't be rich. It'll just be a linear number of different numbers there, because the diagonals are the same, right? Okay, so that's bad. So the addition table is bad. It's not pseudorandom. Let's try what we learned in the second grade, multiplication table. Is this good? No, it's not good. Because it's the same problem. Instead of looking at arithmetic, well, that's not the right. But if you look instead of arithmetic progressions at geometric progressions, you take here 1, 2, 4, 8, and here 1, 2, 4, 8, again, there'll be just a linear number. Okay, so that's not good. So is it an accident that it's no good? Well, many people like to use this quote of von Neumann, who actually needed randomness for his Monte Carlo simulations, who said anyone who considered arithmetical methods, like using addition, multiplication, to produce random numbers is, of course, in a state of sin. So the question is whether we should take von Neumann's advice or not. I will tell you that he didn't take his own advice, and we should forget about it. It's not a good advice. Even he didn't do it, of course. So what can we do? So here's an amazing theorem, and we'll see how to use it later. This theorem was proved first by Erdős and Szemerédi, and in a way that I will not define, but it's in a useful way, was proved by Bourgain, Katzenthal a few years ago. And what it says is while both these tables, well, each of these tables is bad from the point of view we want, together they are good. What do I mean together? If you look at the same window in both, either this guy will be rich or this guy will be rich. If you look at this window in both, the same window in both will always be rich in one of them. And this, you know, even though it's not what we originally want, it turns out to be enough. So let me explain what for. You remember this problem of generating a few independent weak sources of randomness in order to generate good randomness. As it turns out, this is something we did a few years ago after this Bourgain-Katzenthal result. It's very, in some sense, relatively simple corollary of this. Is what you do is you apply this somehow this independence of or orthogonality of addition and multiplication of the basic field operations. And it turns out that what you should do with your samples is just basically, you know, sample from each source, add the first two, multiply by the third. Maybe you need to do it a few times, and that would give you so it amplifies entropy. It creates better and better randomness. And if you do it enough, it creates perfect randomness, which you can use in all the applications I talked about. So it turns out in a world in which you have few independent sources, you can do everything you could do if you had perfect randomness. All right, so that's good. So even if we lost a little bit of gas, you know, we can still do a lot. So let's see what happens if we lose more. The next world is a world where we have some weak randomness, but there's only one such source, right? So sunspots and radioactive decay and stock market and every other of this, the weather, they are all correlated. There is really one source of randomness which is weak. It has some entropy in it, but it's correlated and biased. That's the only source of randomness we have. So what can we do then? Certainly we cannot apply the previous result. And what I'll go, when I'll describe some things that are more technical, they may not be completely clear, but actually they are important results, so I just want to state them. So here's one of the main applications I described of randomness, is that of an algorithm. So we have a probabilistic algorithm. At this stage, the algorithm can be efficient or inefficient. This part will apply to even to inefficient algorithms. But it's algorithms of the type where we have some input data, and we want to know something about it, and we can know it with high probability. Like, for example, counting the number of domino tilings, or knowing whether a number is the prime, or something like that. So there are randomized algorithms for this. And the question is, what can we do if we have, just a weak source of randomness? Well, the obvious thing is not going to work. What is the obvious thing? Is to sample some sequence from your weak source, or some correlated biased sequence of coin tosses, and just feed it to the same algorithm. If you do it, then this is certainly going to fail. It's just too naive to hope, and you can think about it. It's a very simple statement that the naive way of using something that the probability of heads is just 1/10, and tails is 9/10. It would be useless for very simple algorithms that you can devise. So it's not going to work. However, something else works. It's something much more sophisticated, and it uses these extractors, which I did not define, but let me tell you just structurally what they do. So what happens, the right way to do it, and to actually supply enough randomness for this type of application to survive, and I repeat, it's many applications, is the following. You build a different algorithm. It's an algorithm that uses the previous one, but it's more sophisticated. And here's what it does. First, you generate, if you needed here n coins, you generate not n, but maybe n cubed coins, which still have a lot of entropy. I don't know, about n squared entropy. So in qualitative terms, you generate a much longer sequence than you need, and you are guaranteed that somewhere in this sequence hides enough randomness, but you have no idea where. And extractors extract that hidden randomness and make it, purify it, basically. So this extractor, which I'm not going to describe, is a magical object, will create not one sequence, but will create many sequences. Many sequences, not too many, polynomial number. And then what you're going to do is try each of them. Feed each of them to the original algorithm. So each of them will give a result, let's say 1 bit, yes or no. And you try them all and take majority vote. The property of an extractor, so why? So this actually will give you always, will give you the output with high probability, the correct output with high probability. And the reason it does it, or the property of extractors that ensures it, is that when you have a random sequence that's just weakly random but has some entropy in it, what it will generate is a bunch of sequences that most of them will be perfectly random. Most of them, you don't know which, but most of them will be perfectly random. And so when you feed it here, most of the results will be correct, so the majority vote will be correct. That's how it works. Of course, all the cleverness goes into constructing these extractors, and it's a big theory I want to stress. So somehow they generate perfect samples in the sense of the sampling we talked about in the first slide. A sample that has the right, capture the right proportion of the correct answers. And these single source extractors have been developed over the last 20 or 25 years. And what is really amazing is that they were designed, they were born to solve this problem. That was their only, so that was the sole purpose of extractors. And as often happens with pseudorandomness constructions, like this extractor, they found lots and lots of different applications that often have nothing about randomness in them. So this message here is that often creating pseudorandom objects, in some sense, give you benefits that you didn't predict. And here it's being used in complexity theory, in de-randomization, data structures, in creating new error-correcting codes, lots and lots of applications that speak nothing of randomness. And that's, it's a really interesting thing, and it happens not just with extractors, but with other objects, like expanders, for example. Okay, so we covered the one, but the last world. The last world is the most dismal, is the world in which we have no randomness at all. We live in a deterministic world. We have an algorithm that we want to, a probabilistic algorithm we want to run, but this random coins is a figment of our imagination. There is nothing like random coins. Now I'm going to insist that this algorithm is efficient, like polynomial time. So now fewer applications will survive. Only probabilistic algorithms that were to begin with efficient, but those are anyway those that we can implement. So it's not a big loss. So suppose we have a probabilistic algorithm that we want to run. We have our input, but we don't have, what do? We don't have the random. What do we plug in now? So here it is, what we plug in. So that's really a remarkable connection between complexity, again, this computational viewpoint, and randomness. And the message is that computational difficulty can replace randomness, can come instead of it. So if you assume, I'm cheating, if you assume something like P is different than NP, that some of your favorite problems like traveling salesman is hard, or Sudoku or something like this. Just this assumption, if it's indeed hard, if indeed P is different than NP, then we can use it to generate good samples. So just the fact that such a complexity theoretic statement is true is enough to generate from nothing, from no randomness at all, a collection of sequences, again, a small collection, polynomial number, which if you do what we did before, you just try them all in the original algorithm and take a majority vote, this will give you the correct result. And moreover, because now we use randomness at all, if it's a correct result, it's not just correct with high probability. There's no probability. It's correct. So under this assumption, you completely remove randomness from probabilistic algorithm. They remain efficient as they were. If it started polynomial time, it's maybe a slightly bigger polynomial time, and they are deterministic and always produce a correct result. So you don't need, for this kind of applications, you don't need randomness, despite the fact that it seems that you did. You just need that what we believe is true, there are hard problems. Okay, so let's sum up. Let me just mention again, this is generating deterministically a perfect sample. This is the hardness versus randomness paradigm that I mentioned. And this process of generating this sample is called a pseudorandom generator, and many of them were developed. Again, it's a big theory, and the consequence of this is every efficient probabilistic algorithm has a deterministic counterpart. So this, for example, the problem of counting dominoes, approximating the number of domino tiling, there was only a probabilistic algorithm. We don't know a deterministic one, but if P is different than NP, we actually do know a deterministic one. So to sum up, what did we learn? So this important message that randomness is in the eye of the beholder, or the computational power of the beholder. Or basically it's a subjective, it depends on what you're doing with the randomness. It's a pragmatic subjective definition that suits you. You have to consider separately what you are doing with the randomness and see what you need off it. You don't need typically that it's just random. And pseudorandomness, we saw several examples where the different tests or the different uses of randomness, these applications tell you whether you want it to be normal or close to the origin or whatever. And it's a great common area of research between math and computer science. We saw that many of the applications of randomness survive even in a world without perfect randomness, or even without randomness at all. And I also stress that pseudorandom objects that sometimes are born to solve a problem like that find other uses far beyond its original intention. Thank you.